All right. So final talk of Hot UF 2025 is Data Types with Symmetries via Action Containers by Philipp Joram.
Oh, hello, thank you. I'm going to talk to you about containers. I suppose I'm the teaser for tomorrow morning's session, which is also going to be about containers. So maybe this could be considered like one really long session. Let's see. Going to talk to you about what I call, well, action containers. And what I really want to talk about is like how to model sort of like data types a la, let's say, Haskell with symmetries. And, if you think of data types with symmetries, maybe you think of something like, unordered pairs or finite multisets, all those sort of like nice things that you maybe would like to have in Haskell, but you don't. And for that, I'm going to tell you something about, well, a bit of, what containers are, like good old containers. I'm going to tell you the specific kind that I want to talk about. And I want to construct them via, well, some universal property, so that we don't spend too much time on this. And then from this universal property, I want to have some nice, well, properties that we can derive. But since these are slightly more complicated than, well, the usual containers, these have a two-categorical interpretation for reasons that will hopefully become at least understandable. And yeah, so we're gonna also do a bunch of two-category theory. Good old containers are a way of dealing with, well, models of data types in some sense. And what people sometimes have in mind as a model of data types is you think of your type constructors, something like endofunctors on sets, and you think of your polymorphic functions between those data, well, the types they produce as natural transformations. This is a relatively unstructured settings because there's all sorts of wild endofunctors in set. But at least you can describe certain nice subclasses of those functors. And one particular nice subclass is those of polynomial endofunctors. And we can describe those, like in type theory, say, by a container, which consists of a set of shapes and a family of positions over each shape. And we interpret those, as an endofunctor and set. Put in a set X, you get out this big sigma type, which is like a big sum of monomials, if you want to think of it like that. That's fairly well established. But somehow, sadly, not all the interesting functors that we want to look at fit this framework, because I mean, the shape of these is kind of constrained. And think, for example, like something like cyclic lists. So here is a way of defining a functor that sort of like produces like the cyclic lists on a set X. So you take a sum of n tuples modulo some relation generated by, well, a cyclic shift. But you could try and do very similar things for stuff that's like, yeah, unordered pairs or finite multisets, but the cyclic lists are going to be like the running example for this. And, that clearly doesn't really fit what I had on the previous slides, because there was just like, well, a sum of products, and here this is a sum of, well, some sort of quotients of products. Let's see what we can do about this. What I propose, and hopefully this will be clear, like why this might be sensible, is we're just going to take our good old containers, we're going to extend them a little bit with a little bit more structure that hopefully encodes a bunch of the symmetries that are like now going, and like in the previous one, for like cyclic lists, you can think of the symmetries as well. You can identify distinct tuples if you can find some cyclic shift, right? That, shifts one of the tuples onto the others. So we're gonna say that an action container, which is still a set of shapes, and still a family of positions, but now we have extra structure, and that's a family of groups. For each shape, now you get a group. But also all of these groups act on, excuse me, all of these groups act on the positions. So each group element somehow presents a symmetry of the positions. And if you think of this for like cyclic lists, your positions are like the n slots in each n tuple where data can go, and you want to somehow identify different slots, and in this case, well, by cyclic shift. So that's what an action container is. And the symmetries of these things tell us under which permutation the data that is contained from the container is invariant. And this thing also comes with an interpretation like similar to what we did for the standard containers. And it gives you exactly for each, well, in this case, set X, you put in a new set, and it's the sum of quotients of certain products, except that now you can identify two such functions, and under the sigma there, you can somehow find a group element that permutes the domain of these functions. So if you think of an example, in this case, the cyclic lists, you want to write those down as the usual things. So you have n many shapes. So for each length of the list, you get one shape. And for each length of the list, you get like n many positions where to put data. But now you want to identify, let me go back maybe. Now you want to identify two such functions from fin n to x if somehow there's a permutation of their domain, so that you can, well, identify things by a shift. And I can just say, well, I mean, what is the easiest way of like shifting things around? I mean, you can shift things around by an integer amount of, well, steps. So I need an action of the integers on the standard finite set with n elements. And I can just say, well, I mean, adding 1 modulo n generates such a group action in this case. And I mean, actually, in this case, it's enough that I specify this data because, well, it's an action of the integers. I'm going to freely generate it. But this gives me exactly the right kind of identification of these functions of my, well, labeled data. And a similar approach works for finite multisets or unordered tuples or, well, any sort of like, you know, Haskell data type where you'd like to, within one constructor, reorder a bunch of the terms you have there. And by a, well, relatively straightforward pattern. But this seems like kind of ad hoc, I guess, right? I mean, it's like anyone can write down things. Maybe I want to kind of motivate or like why I did it this way. So you can, like, if you recall, like the category of containers, it's in some sense just, well, it's a category of families of sets. So G is category of containers, and somehow it's just, if you look at the very right-hand side of this lens, like a big displayed category where like you have the objects of this thing are sets, and then there's for each set an index family of sets. And this is actually a really nice way of presenting the category of containers. Because I mean, I had to write down some of these things in ACTA, and it turns out if you want to get your proof assistant to talk about like relatively complicated categories, then the machinery of display categories, this is very nice. And you don't have to worry about like some ugly, I don't know, growth and deconstruction that kind of doesn't work so well in tech theory. Or well, it does, but you reprove things that should be obvious. But it gives us sort of like from a description of, oh, how do these things look on objects, the right notion of morphism almost automatically. And also, yeah, ends up being somewhat feasible in type theory. Because you see there's like a big pi involved, for example, and that's just like in writing it down in ACTA, like an actual pi type. I can make nice use of all the dependencies. I define my category of action containers as just a family of actions. So instead of, previously it was like the usual containers are families of sets with some like, you know, trick in the variance, there's like a set up in there. And now I just say, well, a category of action containers is just families of actions, where I have to define, well, what's this category of actions, right? And I say, well, if you usually pick, like you fix one group, you can consider the category of G sets, of like all the actions of the group on like the chosen set. And you can make this slightly more, well, so slightly more variance. You can now just say, well, I have just an action, it's a triple. Also some chosen group, some chosen set, and some action of the group on the set. And you can turn this nicely into a category by, well, what's the morphisms? Well, they map between the groups, group homomorphisms, and they map between these sets being acted on in some way that they are, well, I guess people call this equivariant. But well, the two interact nicely with each other. And it's like a straightforward generalization of just like G sets when you fix the group G. Yeah, this recovers exactly sort of, at least on objects, what I gave you like 2 slides ago. So it gives you these containers, because if you have a look there, everything's just indexed by the set of shapes. But the rest, if you ignore that, is just the data of a group action. But also, since like we construct this category as a sort of like FAM construction, or well, sometimes just called the free co-product completion of a category, we get a bunch of nice properties just for free, which are usually quite interesting. In particular, this is closed under co-products because, well, that's by definition. But also products with a little bit of work. I mean, if you can show that your base that you're taking the families over has products, then this lifts families. But we can also exponentiate by constants in a particular sense. And these are usually properties that people are interested in if they want to say that, oh yeah, our containers actually model somehow some set of inductive types. And what I would claim here is that these containers at least model non-inductive, single variable, strictly positive types as, well, in what sense, right? Strictly positive in this sense means that they're at least well closed under products, co-products, and these exponentiations by constants. That corresponds to your Haskell, I don't know, data type of, well, some types, product types, and maybe some indexing by functions. And these are single variables. So far we like only have a data type that's sort of like parameterized by a single type, like the cyclic lists of a set X, and not data types, let's say like heterogeneous pairs where you have an X and a Y in it, but this is only one variable. But it should be relatively straightforward to generalize this to, well, more variables by some indexing. It's just a lot more work to write it down, but conceptually not much harder. But if you do something like this, you're also usually interested in finding some sort of like smallest or largest fixed point, so to write down some actual inductive data types that can refer to themselves when building the app, like any sort of tree-like structure. But that's kind of missing here, at least so far. And we'll try and get to that. Yeah. And all of this doesn't really come out of thin air. I mean, I just presented to you like that. I mean, what I actually took a lot of inspiration from is what I called quotient containers, which are also about like 20 years old. And at least we can recover this notion of quotient containers. And they're the ones like the subtype of action containers where this action is faithful. And if you've heard of those quotient containers, there you have a selection of groups that you're allowed to identify as the symmetries of your position. So it's like a subgroup of the symmetry group of your positions. And here I can just be a little more general. I can just pick an arbitrary group. But if you restrict to, well, the groups that actually just embed into the symmetries or the symmetric group, then get back your quotient containers. But this has a bit of an unfortunate consequence because, I mean, one of the real nice advantages of the quotient containers is that in, well, this paper where they're introduced, they prove that their interpretation is a fully faithful functor, which means that those quotient containers really specify like a subcategory of interesting endofunctors and sets, fully, and in particular that they fully describe the morphisms, well, the natural transformations, I guess, between those functors. And in this case, it's just like not the case anymore. By some nice and easy counterexamples because I have too many morphisms in this category. And And my interpretation identifies all of those. And quotient containers, they kind of get around by that by sneakily, well, quotienting the set of morphism until it's right. But here I don't do that. So what I'd like to do instead, rather, is I don't want to quotient my sets of morphisms, but I'd like to relate individual ones by two cells somehow in a two-categorical approach. Like keep stuff sort of like a little more structured to keep my evidence around. And I'm going to interpret them in two endofunctors or groupoids, or I guess two endo-pseudo-functors groupoids. And I don't want to go there like just completely from scratch, but I want to go via another notion of container that is known. They're called symmetric containers, and see what we can get out of this. And hopefully also in the process relate these two things. I mean, people have studied quotient containers, people have studied symmetric containers, and sort of intuitively would maybe say, oh yeah, these are the same. It turns out that they're subtly different in interesting ways. So what's a symmetric container? A symmetric container is like where the homotopy type theory comes in, I guess, here now, because you can say, what if you upgrade your shapes to be a H groupoid? So now it's no longer just a homotopy set, but it's just an H groupoid with the same interpretation. And now this interpretation takes H groupoids to H groupoids. But what you think of this H groupoid of shapes as being, you think of it as something that encodes the symmetries that you're interested in, like already on the shapes. So if you have cyclic lists and each shape somehow represents one of the constructors for like lists of length n, then for this particular shape, you think of the paths around it in like a groupoid as, well, the shifts that you're allowed to do to identify different morphisms. So like a nice internalization of the symmetries, like away from a lot of work of like specifying explicit groups. The symmetric containers naturally form a two category. Well, the objects are the containers, the morphisms are the kind of obvious container morphisms you write down, but now equality of container morphisms forms an actual set, like you're comparing functions between groupoids. So the homotopies are a set, and I can just say, well, this is not really a category anymore, but I guess it's a two category or a 2-1 category. And then if you look at the interpretation functor, you stare at it for long enough, it actually forms a two functor from symmetric containers into pseudo functors. So everything's just kind of like now upgraded by one level, and you have to take care of two cells. And that's where the fun begins, I guess. But a similar thing is also true for action containers. You can also upgrade those to a two category. And the two cells there also arise similarly, but like naturally in a way from the idea that you can compare group homomorphisms up to conjugation by an element. Like part of a morphism of an action container is a group homomorphism, and you can just say, well, I don't want to compare those two up like on the nose, but I want to say they are related if there's like some group element that exhibits them as the same up to some conjugation. And this actually corresponds very closely to like this ad hoc relation that's defined for quotient containers that just falls out of, you know, general abstract nonsense somehow. Yeah, but how do we relate those two things now, right? I mean, we have on one hand like the very like set level definition with a bunch of explicit symmetries, and we have this like very nice definition here with, you know, a bunch of H groupoids. But of course, in HOD, you can turn a group into a groupoid, right? I mean, we just heard this. You can take any group G that defines a one object groupoid, or well, a pointed connected groupoid BG. And you do this in cubical character as a high inductive type. And the same construction also extends to a group action, right? If you have an action of G on some set, then this also defines a family from the D-looping into the universe of H sets, where you say, well, by induction, what does this thing do? Well, on the point, if you're D-looping, it assigns the set that you're acting on. And for each loop that you have in the D-looping, it assigns the symmetry that the action gives you in a very straightforward way. So if you take these two things together, you have a group and an action, and this actually defines a symmetric container, because just these 2 bullet points are exactly a groupoid in a set family over it. And it extends to a locally fully faithful 2 functor that takes action containers to symmetric containers. So for each action container like this, I mean, there's the action on like the objects. It gives you sort of like the symmetric container whose shapes are all like a big coproduct of all the delooping of these groups. And for all of these, you just look at the families of sets over there induced by this derived, I guess, family up there. And in some sense, this actually classifies the morphisms of action containers in like a slightly nicer way. Like, remember how I said, like, we don't really get a fully faithful functor anymore into like our endofunctors and sets, but at least here we get some sort of like slightly upgraded setting. We at least get like a locally fully faithful 2 functor into symmetric containers, and from symmetric containers into pseudo functors, we actually have some results that this is actually nicely behaved in an actual 2 categorical embedding. So we get, if we compose of the 2, we actually get some nice interpretation of what our action containers correspond to in terms of functors. But also, if you're not too interested in that, actually is like a really nice way of constructing symmetric containers in practice. I mean, all the examples that I found in the various ways within we described, they all kind of arise this way. So like someone just starts with a collection of shapes and then adds enough symmetries around them in this particular way. Yeah. If you go back to our example of cyclic list, we can now look at what this corresponds to as a symmetric container. So the cyclic list as defined earlier are isomorphic as a container to one that has interesting shapes. So the shapes now are products of natural numbers and things in the circle. And the family of positions over those is n-fold covers of the circle. So over each point in the circle, you have sort of like n many things. And I guess if n is 2, that's called, I think, the junior fibration or something, sort of like the double cover of the circle. So you have like a real nice geometric intuition for like what these things are. And you started out with something very computer sciencey. I found that kind of nice. Yeah. And now for some work in progress on this, I said we wanted to do fixed points, sort of models of like W types or M types. And for those, we want to find some like fixed points of substitution. So we want to think of our data type as giving us a shape of things and like repeated application. And before we even start thinking about this, we have to actually figure out what substitution is for these things. And one desirable property is that this should actually correspond somehow in our intended semantics of functors to a composition of functors, because that's how you plug these things together. And once we have that, somehow the potential candidates should follow from some standard procedure. Like once you have a candidate for the substitution definition, what the largest and smallest fixed points for this operation are should be straightforward. But it seems to be a bit of a problem. Like at least, I mean, I can say finding those is tricky, but I mean, sure, anything can be tricky. There seems to be some indication, though, that the action containers might be a little too strict to encode the necessary symmetries for like how these things now interact if you substitute one of these containers into the other, because you might get interesting interactions between different shapes. But I guess one partial way that I've gotten closer to like trying to figure out why this might not be possible, or if it is possible, how, is the groupoids that we're landing into. Like if you take an action container to a symmetric one, are actually kind of special in the sense that these are all strict groupoids in the sense that they have a bunch of connected components, but all of these connected components are pointed by, well, exactly the base points of these D-loopings. So one way of saying this could be if you have a H groupoid G and you say it's strict, if its set truncation map has a section. So for each point in the truncation, you get a point. For each connected component, you get a point. And this is some idea of like somehow like a category that is skeletal, or the groupoid being a collection of groups. And the nice thing about this is like, even though if you started with like the 2 category of groupoids, if you look at the two category of strict groupoids, like things where the morphisms also preserve the structure, then this actually is one category. So the Hom sets or the Hom types here are a priori not sets, but we can actually prove that they are. If you know the case for pointed connected groupoids, so groups, then this also holds there, and this is sort of like the mini components case of that. This all lifts to symmetric containers. So if you have shapes that are strict, and then you also get a one category of symmetric containers. So like you can avoid a bunch of two category theory now. And I have a work in progress theorem on this where, well, the one category of action containers as defined at the start is actually just the one category of strict symmetric containers. So we somehow carved out a real nice strict subset of those where there's no interesting two cells. My plan, I guess, is if I have any chance of finding fixed points like this, then I should probably look at, well, the right-hand side of it as equivalence, because I know symmetric containers are well-behaved. They have all of the structure. So if the structure somehow preserves the extra pointedness assumption that I have now, then maybe I have a chance of lifting it to that setting. But yeah, that's it where I'm now. For a write-up on this, you can check my website. There's also a formalization of this in cubical agda. So if you want to see a fair share of, well, strict two-category theory in cubical agda, you can, well, check this out and reach out. Thank you.
Okay, so strict symmetric containers should be classically equivalent to symmetric containers, right?
Yes. It is a little tricky to actually write down the right formulation of the axiom of choice that you need for this. Yeah, they might be like merely equivalent in some sense, but yes, they should be. Like, yeah.
Yeah, and also both of them are classically equivalent to Joyal's analytic functors. And those have a really straightforward form of composition that.
Yes, I mean, there is a relatively straightforward notion of composition for symmetric containers, and it's just the standard one for the usual containers, that is irrespective of homotopy level. So, I mean, this is also the thing that I expect to be the right notion of composition, but actually showing that this preserves the extra strictness structure is not so easy.
Or we have time for one more quick question, perhaps. Yeah.
Sorry, I have 1.5 questions. The first one, is it obvious, maybe you said it somehow, that the truncated symmetric container are not the same as quotient containers?
It's not at all obvious that they are not the same.
Okay.
I mean, I thought they were.
Are they maybe, or you don't know?
No, I think I can exactly separate like why they are not the same. Like one of them is just a stricter notion of the others. It's kind of like if you assume that classically each groupoid has a skeleton, then they are up to some minor issues, but yeah. But that's yeah, it's a classical assumption, I guess.
I think my second point, I better take offline, but I just wanted to remark it's also interesting to look at categorified containers, because they're not so strictly positive types like finite sets and truncation, which are not symmetric containers, but which turn out to be categorified containers.
Yes, I mean, these are surely interesting. I mean, this is just a project that lends itself very well to working inside of HOT, because everything is kind of symmetric. So it's just like a real nice target to talk about these things. But of course, there's other more directed generalizations. Yeah.
All right, let's thank the speaker once more.